we're going to look at a question involving conditional probability. This particular question relates to the law of total probability and Bayes' theorem, although this terminology is not actually specified within the WJEC Unit 4 syllabus. However, the concept of conditional probability is very much in that syllabus. In probability theory and statistics, Bayes' theorem describes the probability of an event based on prior knowledge of conditions that might be related to the event. The question that we will look at is very traditional of this sort of situation. It is known that 5% of animals of a certain species have a particular disease. A diagnostic test can be applied to the animals of this species to indicate whether or not they have the disease. When applied to an animal which has the disease, the test gives a positive result with a probability 0.96. When applied to an animal which does not have the disease, the test gives a positive response with a probability 0.02. So we have prior knowledge of a diseased or not diseased, which therefore affects the probability of a positive result. The test is applied to a randomly chosen animal, and we're asked to calculate the probability of a positive response. To do so, a tree diagram is a very useful tool. This is not essential, but it does help to summarize all the information in one place. So diseased, not diseased, 0.95, 0.05, of course that's 1 minus the 5%, and positive given disease, 0.96, given in the question, 1 minus it, 0.04, 0.02 is positive not diseased, and 1 minus it is 0.98. We're going to apply what we call the law of total probability. Again, the terminology is not essential, but the concept is very simple. For a positive result, we can obtain a positive given diseased, or a positive given not diseased. The multiplication of diseased and a positive given diseased gives the probability of a diseased and a positive result. Similarly, diseased and not, positive and not diseased, 0.95 multiplied by 0.02. And since these events are mutually exclusive, we can add these probabilities together to give our total probability of 0.067. In part 2, we are now given a condition. We are given the condition that a positive response is obtained. We're asked to find the probability the animal has the disease. I'm going to apply the formula for conditional probability. This is actually Bayes' theorem, but again, the terminology is not important here. The probability given a positive requires us to divide by the probability of a positive result. Of course, this is 0.067 from earlier. On the numerator, we have the probability of the two conditions, diseased and positive. And of course, this was obtained partially from the calculation above in part 1. So diseased and positive, 0.05 multiplied by 0.96, this gives us our numerator. Dividing gives us the total probability conditional upon a positive result of a diseased animal, and that's 0.7164. This figure will be useful in part B in one of the approaches that we can use to answer the question in part B. So let's consider the situation in part B when we give the chosen animal a second test. However, we are given the fact that a positive response was obtained in the first test. So we can extend our tree diagram to establish the various different options of the things that can happen. But since we are given a positive result, we really are only interested in these two branches of the tree, diseased positive positive, not diseased positive positive. Find the probability that it gives a second positive response. Of course, we have a condition here. We are given a probability that the first has given a positive result. So we apply our formula for conditional probability again. Given that the first is positive, we will divide by the probability that the first is positive. That's important, very easily missed in this sort of question. On the numerator, we want the second and the first to be a positive result, and this is obtained by multiplication along the branches, the law of total probability, 0.05, 0.96, 0.96, disease positive, positive, 0.95, 0.02 times 0.02, not diseased, positive, positive. Adding on the numerator the two different options and dividing by the denominator, which is the probability that the first is positive, gives our conditional probability that the first is positive, the condition that we get a second positive response. 0.6934 is the required probability. Now in part B, part 2, we are now given that this second response is also positive. So in total we have positive first and positive second. They are the conditions that have been given. We're asked to find the probability this animal has the disease. So we're looking at, given the probability that both are positive, what's the probability of a diseased? Applying the rules of conditional probability, on the denominator is the probability both are positive, and on the numerator diseased and both positive. Now all these figures can be established from the tree diagram or have already been established. So the probability that both are positive, that's what we obtained earlier by multiplying diseased positive positive and then adding the multiplication of not diseased positive positive, and that's giving us 0.05, 0.96 squared plus 0.95 times 0.02 squared. On the numerator, of course, we're only interested in diseased and both positive, so that's the 0.05 multiplied by 0.96 squared. Dividing the two gives us the conditional probability of being diseased given that both were positive of 0.9918. This is a high probability, relatively, and this is not surprising, seeing as our animal has given two positive results, and therefore it's increasing the chances that it actually is diseased. Of course, there is a small chance that statistically this has been obtained as two positive results, but actually the animal is not diseased. There is an alternative approach to part B, which we will look at very quickly, and it utilizes some of the figures that were calculated earlier. Earlier we worked the probability of diseased given positive. Now if we classify this as a first positive result, this is really the condition that has been given in B part 2 of the question. That was 0.7164. So the probability of not diseased given a positive will be 1 minus this figure. So we can condense the tree diagram into just these two outcomes there. Diseased given positive, not diseased given positive, 0.7164, and 1 minus it as 0.284. We're then looking at the second response, and we're after a positive result, in which case we can find the probability of the first and the second as being positive, which is what we required in B part 1, by multiplying 0.716 by 0.96, diseased positive and positive, not diseased positive and positive, 0.284 multiplied by 0.02. 0.6934 is the same probability we obtained earlier in our previous slides. If we look at part 2, again we can apply the conditional probability of diseased given that the first and the second are positive. On the denominator we have first and second being positive, which is 0.6934, and on the numerator that's the positive on both and the diseased, so 0.716 multiplied by 0.696, giving us the same probability of 0.9918. The mark scheme of the WJEC in this particular question did actually utilise this approach, but there was an alternative that we could use by extending the tree diagram.